Here we present our experiments in air-ground robotic collaboration with SPOMP. Our first site, Panoramic, is a relatively urban environment. We employ 3 ClearPath Jackal UGVs, each equipped with a 64-beam Ouster LiDAR. We also use a custom Falcon 4 UAV, which acts as an eye in the sky and communication relay. The environment includes challenges such as curbs, varied terrain, and ongoing construction. In these experiments, the UAV will build an aerial map of the environment in real time, which the UGVs will simultaneously use to identify goals, in this case vehicle clusters, and navigate to them. A fixed base station acts as a communication node, but does no computation. The UAV flies an initial exploratory path while building an aerial semantic map. UGVs identify goals in the map, in this case clusters of vehicles, shown in cyan. We can now see the paths planned by the UGVs, and the first UGV beginning to drive towards its goal. Note also the green lines between robots showing they have a communication link, and the blue line when they complete synchronizing data. We now focus in particular on UGV2 and its perception of the environment. The aerial map from the UAV can be seen on the left, along with the overlaid topological graph used by the global planner. The lighter the edge, the easier the robot believes it is to traverse. On the right is the learned traversability map. Light green and red are traversable and untraversable areas experienced by this and other robots, and the rest is extrapolated based on the aerial map. This map informs the topological graph weights. Going back to view all the robots, we can see UGV1 with its yellow path, camera view, and traversability map. We can see the same for UGV2 with an orange path, and UGV3 with a red path. Notice how the robots deconflict goals automatically. We now focus back on UGV2. The green edges in the traversability graph are edges that this robot has traversed successfully. By contrast, red edges are those that the robot has observed to not be traversable. The robot automatically replans to find a new global route if the robot observes an edge to not be traversable, or the extrapolated traversability changes. On the right, we see a visualization of the UAV planner. The yellow line here is planned by the UAV to reach its best knowledge of one of the UGV locations. Now that it has successfully synchronized with that robot, it plans back to where it was, and then continues following a pre-planned coverage path. It will do this for a set duration before seeking out a different UGV to communicate with. In this way, the UAV acts as both an explorer and a communication relay for the ground robots. If you draw your attention to the 3 robots' traversability maps on the right, you note that UGV2 is currently exploring to the west. It is therefore adding new information to its map that is not visible in either of the others' maps. However, if we wait, we can see a blue synchronization line appear between UGV2 and UGV3. Simultaneously, the traversability data from UGV2 appears on UGV3's map. This occurs because the two have now synchronized their experiences and incorporated them into each other's maps. Note that all robots are operating entirely autonomously, with the UGVs having no GPS, but instead using the aerial map to localize themselves. Safety pilots are only there to interfere if needed. For the rest of this video, we will let the experiments play out, occasionally adding commentary for interesting behavior. Focusing on UGV2, we can watch a particularly difficult planning scenario. There are a number of construction road dividers not visible in the aerial map, as well as complicated terrain structure with lots of curbs and ramps. At several points, the safety pilot takes over to pause the robot and move out of the way if needed of passing vehicles on the road. The robot keeps trying new paths, but finds them blocked until it eventually finds a safe route. Once it has found this route, it follows it to autonomously navigate to the goal. In order to return, it now just backtracks on the graph edges that it now knows to be traversable, doing all this autonomously as well. We additionally performed 2 other experiments in the same environment, with one of them using a different starting location for the robots. Between these 3 experiments, the UGVs travel a combined distance of 13.7 kilometers autonomously and visit 41 out of 42 goals. Our second environment, the New Bolton Center, has its own set of challenges. This environment is more rural, incorporating more grass and trees, as well as significantly hillier terrain. For this experiment, the UAV does not operate simultaneously with the UGVs, and we instead give the UGVs the aerial map in advance. Note that this robot's initial global plans look somewhat odd due to the minimal terrain experience that it has. However, the robot quickly learns that roads are good to drive on and comes up with a more logical route. Despite the absence of a UAV during this experiment, UGVs still communicate with each other as well as the base station. For the rest of this experiment, we focus on the perspective of UGV3, since its behavior is the most interesting. Here the robot is able to successfully autonomously navigate down a grassy hill on the basis of the aerial map. When returning back to the hill the robot drove down earlier, it determines that it is too steep to climb back up. However, the robot is nonetheless able to identify a shallower path up the hill and still autonomously reach its goal. Over the course of this experiment, the 3 UGVs traveled a combined distance of 4.1 kilometers, reaching all 8 identified goals. Finally, we perform a number of simulation experiments with up to 10 UGVs, as in the one shown here. The entire autonomy stack is running here on each simulated robot, with the exception of localization and semantic segmentation, both of which are provided directly by the simulator. We demonstrate through these experiments that our system scales well with larger team sizes. Note in particular how the robots automatically distribute goals between themselves. For more information about this work, please see the video description below. We open source our system as well, the code of which can be found here.